All right, today we're going on a quest, a quantum-enhanced quest, to be exact. Our goal? To find something that sounds simple but is incredibly hard. A perfect sequence.
So imagine you're designing a radar system, right? You send out this pulse, this signal, and you're just waiting for it to bounce back. But here's the problem. The signal itself can create these little ghost echoes that are just slightly out of sync, and that's super confusing for the system. So the big question becomes, how in the world do you design a signal that's so perfect it doesn't create its own interference?
Well, this challenge actually has a pretty formal name. It's called the Low Autocorrelation Binary Sequence Problem, or LABS for short. Now, all that really means is we're trying to find a sequence, just a string of plus ones and minus ones, where the energy of its own echoes is as low as you can possibly get it. Think of it like this. How much does a sequence overlap with shifted copies of itself? We want that overlap to be practically zero. Okay, so the whole game is about minimizing this one value we call energy. You see the formula there, but don't worry too much about the math. Just think of it as a score. The lower the score, the better the sequence, the fewer ghost echoes we have. Our entire mission, our whole quest, is to find the one sequence of pluses and minuses that makes this energy number as tiny as we can, using every tool we've got, both human and quantum.
So, here's our game plan. We'll start by really digging into this quest for the perfect sequence. Then, we'll meet the incredible team they put together to solve it, a quantum classical hybrid. We'll look at the quantum seed generator, then the classical refinement engine. After that, we'll see how they work together, and finally, we'll talk about what this all means for the future.
So, when you're faced with a problem this difficult, what do? Well, the answer here wasn't to just throw one type of computer at it. Nope. The strategy was to build a team. A hybrid team that combines the totally different strengths of quantum computing and good old classical computing to take on this challenge.
And this is where it gets really cool. Think of it like a two-person expedition into a huge unknown wilderness. First, you have the Quantum Scout. Its job is to fly high above the landscape, surveying everything. It performs this massive global exploration, quickly spotting the most promising valleys and clearings from a bird's-eye view. Then you have the Classical Explorer. Its job is to rappel down into those promising areas found by the Scout and get to work, meticulously mapping every detail, refining the path, and improving the camp step by step. One explores, the other exploits.
Okay, let's talk about our Quantum Scout first. In the code, its official title is the Quantum Seed Generator, and its whole mission is just that, to find the absolute best starting points for our search.
So how does it do it? Well, it's a four-step process. First, it samples thousands of random sequences, just to get a feel for the landscape of the problem. Then, with that info, it builds a schedule, basically a detailed plan for what comes next. Step 3 is the real quantum magic. It evolves a quantum state, which is a simulation that kind of naturally pulls the search towards really good solutions. And finally, it measures that final state to pull out a bunch of high-quality seeds. These are our starting points.
But, there's a catch. This quantum approach is super powerful, but it's also a memory hog. It's incredibly memory heavy. See, the amount of data you need to simulate that quantum state just explodes exponentially as the sequence gets longer. What that means in practice is that this whole Quantum Scout thing is really only feasible for shorter sequences, maybe up to a length of 20 or so.
All right, so the Quantum Scout has flown over the landscape, dropped its flags on the most promising spots, and delivered a set of excellent seeds. Now it's time for the Classical Explorer to get to work. Let's meet the Classical Refinement Engine. Its job is to take those seeds and just make them better, relentlessly.
And it's got a few really powerful tools to do this. For one, it can combine. It takes two good parent sequences and mixes their traits to create a new child. It can also mutate, which is just making tiny random changes, like flipping a +1 to a -1 to see what happens. But the cleverest tool by far is something called a taboo search. It's a really smart way to keep the search from just going around in circles.
So what exactly is a taboo list? The best way to think about it is like giving the algorithm a short-term memory. It literally keeps a list of the last few changes it made, and then it makes a rule, you're forbidden, it's taboo, to immediately undo those recent changes. And this is just brilliant because it forces the algorithm to go explore new places instead of getting stuck just flipping back and forth between two okay-ish solutions.
Okay, so we've met the Quantum Scout and the Classical Explorer. We know their jobs. Now let's put it all together and see how this team actually works in the main algorithm.
So it all starts with initialization. Our Quantum Scout does its thing and generates the starting group of sequences. Then the real work begins, this loop that just runs over and over. First, it selects some parents and creates a new child sequence. That child is immediately handed over to the Classical Explorer to be refined using that clever taboo search. Then it gets evaluated. Is this new, refined child better than the best one we found so far? If it is, it gets to replace a random member of the current population. And then we do it all over again, and again, and again, for thousands and thousands of generations.
And this right here, this is the beautiful synergy at the heart of this entire thing. The quantum part gives you the creative leap, that big picture exploration to find totally new, promising areas you might have missed. Then the classical part comes in with the disciplined refinement, the relentless step-by-step work to perfect those ideas. It's the best of both worlds.
So, after all that elegant teamwork, what was the result? Did the quest succeed? And maybe more importantly, what does this tell us about the future of solving these kinds of crazy hard problems?
All right, so the algorithm was put to the test on a very specific problem. Find the best possible sequence with a length of 16. And they let it run that improvement loop for 1,000 generations.
And the final score, the best energy value it found, was 28. Now remember, the whole point from the very beginning was to get this number as low as possible. By combining that big picture quantum exploration with the nitty-gritty classical search, the algorithm landed on this remarkably low energy score.
And that really leaves us with a fascinating, kind of mind-bending question, doesn't it? This Quantum Scout and Classical Explorer team, it worked incredibly well for this one really specific, really tough problem. So you have to wonder, what other massive, complex problems out there could this powerful hybrid duo solve together? I mean, think about things like drug discovery or creating new materials or even financial modeling. The possibilities are pretty amazing.